Okay, this is lesson 5.1, solving systems of linear equations by graphing. So as defined in your book, a system of linear equations is a set of two or more linear equations in the same variables. Here's an example. X plus y equals 7 and 2x minus 3y equals negative 11. The solution of a system of linear equations in two variables is an ordered pair that is a solution of each equation in the system. So for example 1, we're going to tell whether the ordered pair is a solution for this system. And the way that we do that is we substitute in the values and we check the work to see if they work. So for the first one, we would substitute in a 1 for x and a negative 2 for y. And then we'll substitute it in for the second one, so it works for the first equation. So if we have the opposite, then I'm actually doing the math on the left. Negative 1 plus a negative 4 is a negative 5, and that does not equal 5. So for the first one, the answer is no. The solution is not, the ordered pair is not a solution. For number 2, again, substitute it in, so you have x comma y. So 4 is equal to 3 times 1 plus 1. And that's true. For the next equation, 4 would be equal to the opposite of 1 plus 5. And that is also true. So for number 2, yes, the solution would be, the ordered pair 1 comma 4 would be a solution for this system of linear equations. And if we were to graph them, that would be the point at which the two lines would intersect. Okay, so our core concept is step 1. You could, by graphing, you could graph each equation in the same coordinate plane. 2, estimate the point of intersection. And 3, check the point from step 2 by substituting it in for x and y into your original system to make sure that it's a solution. So you may want a straight edge and graph paper when working through these problems. So for the first one, we could go ahead and just graph it using the slope-intercept form. So if the y-intercept is negative 2, and my slope is a positive 1, I'd write at least another line, and then it's going to be hard for me to draw the line. Okay. And then look at the other one, the other line. We have a positive 4, and if it's a negative 1, and when I draw this line, I don't know, it's really hard to tell because I've drawn the line so thick, and of course I'm not using a straight edge. Use a straight edge for accuracy. The point that I see as intersection would be 3, 1. And so I would check my work. I would come up here to the original equations and I would substitute them in. For both equations. And I see that they both work, so 3, 1 would in fact be the solution. Okay. Again, graph the line. I'll try to use some thinner lines this time, see if that'll help. So no, it does not. Okay. Okay, and I'll change colors before I actually draw the lines. I'll graph the other one. At -5, and then I have a negative slope. Okay, good. We can kind of see where these two lines intersect because I have a point down at -4, 1 for both of them. So then I'll go back through and I'll draw the line for both of them. Again, use a straight edge. Okay, here's this point of intersection at -4, 1. So I want to check the work, make sure that it actually is truly a solution. Worked for the first one. Let's look for the second one. And it worked for the second one. So again, using a straight edge to make sure that you're getting as accurate as possible so that you can estimate the solution set based on where the two lines intersect. And for this one, I want to go ahead and I think it'll be easiest if I change them to slope-intercept form. So for the first one, I will rewrite it by subtracting 2x on both sides. So I'll get y is equal to a -2x plus 5. And in this one, if I subtract 3x, and come back and divide by a -2, I'll get y is equal to 3 over 2x minus 2. And again, go ahead and graph using the slope-intercept method. So for the first one, we have a +5 and some points along the way. Okay. And if I switch colors here, and I graph the next line at a y-intercept of -2, I can see that this is where my, okay, so here's this line, and my green line, the first line, is right there, and this is the point of intersection, which is at 2, 1. And so then I'll substitute it back in. So I'll get 1 is equal to negative 2 times 2 plus 5. And I'll get 1 is equal to 3 over 2 times 2 minus 2. And it does work out for both, so 2 comma 1 is indeed the solution where the two lines intersect. If you make a mistake and your graphs aren't straight and you estimate or you even graph them incorrectly, it won't be a solution for both of them. So there will be at least one solution that satisfies both equations. So for your homework, you'll be on page 239, working on numbers 3 through 20. All this is also available for you online at bigideas.com.